ideas and on pregeometric theories and their relevance to quantum gravity. I'm particularly going to focus a little bit on the synthesis between physics, mathematics, and computer science, from where these ideas are borrowed, and some recent work as well. So without further ado, let me just get started. This work is in collaboration with Dean and Hatem. The work is still in progress, but there's also some previous papers from the Wolfram physics project, from which a few ideas are being borrowed. So essentially this will be a connection between physics, computer science, and math for the purpose of answering the question, where does space come from? When we think about models of space and time, we take it for granted that there's some geometry or etc. So I want to really ask, where does space come from? How can we build space, if at all? And so some of the early motivation comes from the work of this idea of pregeometry by John Wheeler. He was the one who coined this term. And for him, as such, pregeometry is something which is some kind of structure that should neither have topology nor geometry. Particularly, it should not have any sense of metrics or everything, any sense of metrics or distances, etc. No spatiality somehow. So it's a little hard to imagine as a physicist, what would that be? If you think of any physical object, it almost always has some notion of geometry or some kind of topology at least. So some abstract entity which is neither topological nor geometric, what should it be? And Wheeler himself had in mind that this might be something more abstract than the physical. He was thinking of something in terms of a propositional calculus, or what in modern terms people would describe as a formal language. So the kind of key here is that formal language will give us a mathematical tool for coming up with some kind of foundational framework for describing pregeometric structures, which might then inform current theories of quantum gravity. So we want to think of pregeometry as literally building blocks of space, or ask the question, where does space come from? And at that time, Wheeler had, these were some of Wheeler's motivations, that this structure had to be something that's not necessarily physical. Most theories of physics assume some physical ontology. He wanted to go something that was almost pre-physical. In a way, he had this idea in mind that instead of thinking of space in the way, space and time in the way we do, where there is some structure and then we apply various procedures like quantization or whatnot, Wheeler was kind of asking the question, how does nature construct space-time itself? Or in a way, if do we have something where this construction is fundamentally constructivist? I'll say a little bit more what constructivist is. Constructivist here is really alluding to constructivism in the sense of computer science, or in the sense of constructive mathematics, where you do not use proofs by contradiction, or you do not use proofs by assuming that if it's not this option, it's that. You have to construct the system as to show that that particular property exists. So Wheeler had something like this in mind, but at that time the mathematics for expressing these ideas were not there. And now only recently we have ideas from homotopy type theory, higher category theory, etc., which might give a mathematical home for expressing these ideas. So besides this motivation that Wheeler had, there was some more concrete work done in around 2007, 8, etc. by Chris Isham. Paul Davies already referred to some of Isham's work. So Isham was one of Isham and Jeremy Butterfield and his collaborator Andreas Doring, they were among the first few people to start taking this topos theoretic view a little seriously. I'll say in a minute what a topos is, but here let's talk in terms of thinking of category theory. So they started taking this view of category theory very seriously for expressing foundations of physics. They were not really thinking about geometry yet. That question was a little more complicated, and in fact even at that time the mathematics was not there. So what Isham and Doring and others were doing is they were trying to ask a sort of what would be some kind of formal meta theory within which you could express various models of physics, in which you're not assuming that continuous quantities exist like real numbers, complex numbers. They wanted to allow for some description, some structural framework where you might even have notions of discrete quantities. It could be space-time or it could be observables, but they were saying that if you wanted to really assume a setting of a discrete setup, what type of theories of classical mechanics, or how do the laws of physics, classical mechanics, quantum mechanics, etc. look like. So they came up with this framework in category theory. Topos is a special kind of category. I'll say in a minute what that is. But within this abstract setting of category theory that mathematicians often use for expressing generic quantities in mathematics, for even expressing the foundations of mathematics, the idea was that for Isham and Doring, that these structures admit the description of a formal language, and this formal language is the meta theory through which you can express classical mechanics, quantum mechanics, and so on. They were just sticking to classical mechanics and quantum mechanics. They were not thinking of quantum gravity or space-time in that sense. So they had this formal language in mind. Now, Wheeler had similar ideas, but Wheeler was talking about some sort of propositional calculus, where he was thinking in terms of propositions and the logic of propositions. Here, what Isham has been used was what is now known as type theory, and its advanced versions would be higher type theory, etc. Those things I'll come to as we get on. So just a brief interlude on what I mean by toposes here. I try to keep this description in a generic way, but of course you can, those who are more mathematically inclined, there are more details. I'm trying to just give the main ideas here. So toposes are categories that behave like sets. Now, in standard mathematics, a lot of the foundations is based on set theory, ZFC set theory. And set theory is a good place for doing mathematics. In a way, you can understand what's one nice property about a set is that you think of a set with its elements, etc. There is no notion of continuum in there. It's just discrete objects, entities, and that's a good setup for doing a lot of mathematical foundations. But it's not the only one, and there are reasons why it might not be completely satisfactory, especially when you think in terms of computer science. In computer science, you need these notions of constructivism and proofs where you can only prove something by constructing that property exists. You can't assume that a proof by contradiction, which is to say that you don't assume that if either a proposition is true or false. If you prove that it's false, then the negation has to be true or something. There could be something in between true and false, which could be just undecidable, and a lot of problems in computer science are undecidable. So over here, what we mean by toposes are categories that are not necessarily based on sets, but they have properties which are like sets, in the sense that in the category of sets, you have a notion of sub-objects, which are the categorical analog of subsets. In toposes, you have, even though toposes, so the bold letter sets, which means a category of sets, has objects as sets and morphisms or maps as functions between sets. But in other categories, the objects might not be sets; they might be other things. However, if that category, those new categories have certain properties, like they allow some analogous notion of a subset, an analogous notion of a singleton set, an analogous notion of an empty set, etc., then they have very set-like properties, and then you call those are the things that you call toposes. And one of the advantages of a topos is that in toposes, you have this nice property that when you look at the algebra of its sub-objects, I'm just using the word subsets as analogs because you don't really call them subsets, but when you look at the algebra of these quote-unquote subsets, they satisfy a generalization of Boolean logic. In typical set theory, when you're looking at subsets and you look at all kinds of logical operations you can do with subsets, you use Boolean algebra. In toposes, they admit a generalization of these Boolean algebras to Heyting algebras, and the key difference over here is that these Heyting algebras allow for the law of the excluded middle not to hold, as in you don't have to, a proposition doesn't have to be true or false, it can also be undecidable. And that is the foundation of what people use in intuitionistic logic, which is deeply embedded in computer science, where you have computational problems where a proposition may be undecidable, or a problem may be you might not be able to decide whether that problem will terminate or not computationally. So in the foundations of mathematics, people often work with toposes as places where mathematics can be done. So now, the main takeaway here is that instead of basing physics, a lot of formal theories of physics are based similar to formal theories of mathematics. Now, in the same way, like in mathematics, people realize that instead of working with set theory, we should work with something more abstract and more general. Isham and Doring and other people took that idea seriously in physics as well. They said in physics, let's use these type of toposes that people in computer science and foundations of mathematics use, and ask how you can formalize theories of physics where you do not have to assume notions of real numbers or complex numbers, where you might admit for physical observables having values that might be from some discrete set or something. So what they, in this meta framework, what they did is they said that, well, on toposes, toposes basically allow you, they admit some formal language to be expressed within them. The formal language allows you for all kinds of operations, some sort of proof systems, logical operations, etc. And one of the two formal languages that they tried in their early works, of course, this propositional calculus that Wheeler and other people had already discussed, but they also tried what are called these type theories. I'll say a little bit more about what type theories are. Again, a type is, at this point, just think of a type as something analogous to a set, but with some specification, or in a way you can think of a type as a data type. So type theory is a framework that allows much more expressibility than a standard propositional calculus, and all modern day formal languages nowadays are founded on type theory. So I'll have to tell you a little bit about what type theory is about. But just before we get to that point, what this topos theoretic framework was doing is that, well, they said that you work within some you formalize a theory of physics like classical mechanics or quantum mechanics as a formal language, and this formal language will be expressed in some topos. Within this topos, which is a category in a sense, you have some notion of a state object, which is like the analog of the state space, and then you have a quantity value object, which is the analog of values that physical observables can take. So they thought of physical observables as morphisms or maps from these state objects to quantity objects. Now, in category theory, when you speak about maps, you only speak about it as a higher level, in the sense that when we talk about ordinary set theoretic mathematics and we speak about functions, we talk about domain, codomain, we talk about the elements within. In category theory, people don't talk about the elements within. You talk of the whole object, the whole domain as the object, and you talk about higher level maps between the objects. So you have to do a little more work to say what might be the analog of elements, what might be the analog of subsets. But over here, the kind of argument they are trying to base is also keep in mind that this framework of Isham and Doring is not meant to capture all of physics in the sense. It's most of what they say over here is kinematical statements. The goal that they try to their goal over here is to try to give a general framework to be able to express what physical observables are and to be able to reason about them. So in the sense that what they can do over here is, you can if for example, if you have this this particular observable A, whatever it might stand for, the observable A is a map from the state object, the analog of state space, to some quantity value object. Now, when you're talking about specific when you're talking about specific states of the system, there will be subsets or sub-objects within the state space, and they might map to some part of this quantity value space. So the physical observable is associated to some analog of the subsets of the state space. So in that sense, these subsets are equivalent to propositions about that state. Propositions in the sense that it expresses the fact that this physical quantity being a subset of state space and mapping to a subset of the quantity value space is saying something about the system. And if you have several such propositions, you might even start doing logical operations upon them, which means that you take one subset, you take another subset, and you might perform the union or intersection, and then ask if something is true or not.
Sorry, are you taking questions during the talk?
I would prefer at the end, but if there's something like
it's
a notation.
Question.
Sorry?
It's a clarifying question.
Okay.
Does the relation of containment apply applies to these sub-objects. But can you say that this object contains this sub-object, yes or no, or maybe with this?
So I don't think they went that far to discuss that. What they do is so far in this work, they just try to discuss unions, intersections, and those kind of things. Entailment would be, for entailment, you would have to express a little more. In principle, you could do this in this framework, because if you have sub-objects, you have global elements, you might try to read off the global elements of these two subsets and try to see which ones are intersecting or not. So you might be, with a little more work, you might be able to set up entailment.
Does the excluded middle hold or not hold for containment?
Right. So over here in their setup, they are trying to say they are trying to work in this framework, not in this framework. What this statement is saying is that if a proposition alpha, either it is true or false. In the whereas when you're working with intuitionistic logic and in the constructivist framework, something can true or false are not the only options. You might have the undecidable options. So when you're working with this, you have to be a little bit careful, because also when the law of excluded middle doesn't hold, double negation is not equal to the proposition itself. So one has to be careful when you're. I think the only issue is that when you're trying to say something is contained within none, you have to care about the boundary. So that's the issue. And when you're working in the standard Boolean setup, one thing is a complement of the other. Whereas when you're working in the intuitionistic setup, you have to care about the boundary. So I think that's the complication to take care of. Yeah. So essentially, the kind of attractive feature of working in this generic topos framework is that it allows you to work with logic more general than Boolean logic, which is intuitionistic logic. And computer scientists are well aware of this. They already, in computer science, a program which is like a set of instructions to get from one state to another state, you have to actually construct it, and the program is the proof that this initial state and final state are equivalent. And that's the kind of constructivist approach, and it's based it is based on this in many of those formalisms of modern day programming languages. They are indeed based on intuitionistic logic, where this scenario holds, not this. That is, the law of the excluded middle is not valid. So in this framework, now you might say, why did they go to the trouble of working with this setup? Essentially, the key point over here is that Isham and Doring and other people are making is that if you borrow these ideas and stick to this framework, you do not have to assume, you do not have to work in the setting of the reals of the complex numbers. You can work in settings where these quantity value objects over there, they might be from some discrete set, or they might be something else. You don't necessarily, you could still work in the set theory framework with assuming that this is real, or etc. for some standard theory, but you could construct mechanics and quantum mechanics in setups where the real numbers don't hold, or where the space that you're talking about is fundamentally discrete, with the idea that if you wanted to really ask what mechanics and other things would be like in discrete space-times, then this would be a possible framework to express some kinematical assertions about that type of world. So this was the proposal. Now let's see how far one can go with this. Obviously, they didn't say much about dynamics, and they didn't really say anything about space-time or quantum gravity models. They were not even worrying about pregeometry in this paper, as I said. They were just trying to say that if you have to express kinematics, how would you express kinematics? The answer is kinematics can be expressed in terms of some formal language within some appropriate topos. And just to give you a contrast, in classical mechanics, they said that the relevant topos is still the category of sets, whereas in quantum mechanics they identified a different category, a different topos, which is related to operators of a Hilbert space. I know that in this audience there are some people who are working in categorical quantum mechanics, so I'll just make this comment, which we can discuss later, it's not too relevant now. In categorical quantum mechanics, which is also a very category theory approach based for doing some version of quantum circuits and quantum computation. This is a different category that one is using, which is the category of finite dimensional Hilbert spaces. Whereas in Isham's approach, you're using the category of pre-sheaves of operators on a Hilbert space. So there are some different type of. In fact, the second one is the lower one is not even necessarily. I'm not, if I'm not mistaken, is not even a topos. But here the goals were different. Here the second framework is used more for quantum circuit simplification and other goals. And nonetheless, I'll point out later on for what this other alternate category theory approach might be relevant. So this is just to point out that there's a selection of categories within which one can set up these models and compute processes, where in all these cases, including in categorical quantum mechanics, you're not assuming any background space-time. In a way, all these attempts were to get rid of some continuous background or even some background. Even though these theories didn't speak about space-time, we'll borrow some of these ideas to actually talk about models where indeed you can escape this notion of continuous backgrounds or backgrounds at all. So just a kind of overview, what do we mean over here by formal languages? By formal languages, we will be referring to well-formed strings over some alphabet, where the strings are constrained by some generative grammar. These are rules that tell you how to compose the letters to form the words of a language. As such, this is a very a formal language in mathematics is a very general concept. You might want to equate it to some sort of universal algebra. In a universal algebra, you might have similar things. You might have a base, the universe of base objects, which gives you the alphabet, and some rules for how to make words out of these alphabets. But the more interesting formal languages, you can have a little bit more. Instead of just having strings, you might even want to use this thing for theorem proving purposes, which is what you might do in a lot of setups that you're working with, at least from a mathematical point of view. So there you might additionally, besides these rules of how to form words, you might additionally equip the language with some axioms and inference rules, and that becomes your proof system. And these proof systems will then be useful for proving theorems, not just about forming words, but you might even say when two words are equal or when combinations of words can be formed together. So here, when you have a formal language equipped with a proof system, that is what we will call a computational language, because that is the language within which you will be able to do theorem proving. And for both computer science as well as in lot of form of logic, etc., these computational languages are the things that mathematicians use for theorem proving, especially in the context of constructive mathematics, where the proof is the proof of a property requires construction of that property, and you cannot prove it by contradiction. One comment to this, when I hear, I of course given this definition as is often as you find in several sources in terms of strings, but more recently we know that these formal languages need not only be languages where these strings are terms of some symbols written linearly. A lot of the times, in fact, now there are lots of examples where these the alphabet or the strings can be graphs, hypergraphs, higher dimensional diagrams, even operators, and this gives you a rich extension to what formal languages are. You might have graphical languages, diagrammatic languages, operatorial languages. In fact, in categorical quantum mechanics, the quantum circuit diagrams, you could think of those as words. They could, depending on the specific conditions, those quantum circuit diagrams are sometimes called string diagrams. They are two-dimensional diagrams, and you can in fact have languages, diagrammatic languages, where graphs or diagrams or even operators themselves form the symbols or themselves form the words, and it's like a two-dimensional language. It's like a pictograph. You're not just working serially in a line, but you might compose things vertically as well as horizontally, or if the thing is a diagram in higher dimensions, you might compose things in multiple ways. So there are rich notions of formal languages that can exist, and some of these notions we will allude to in what we are setting up. So let me say a little bit about type theory. Type theory is a general framework of it's a general framework for specifying formal languages. You have to specify what language you're interested in, and the kind of idea is that there are many types of languages you can build depending on what problem you're trying to solve, what the setup is, and those languages will be you have to build them up in a particular way. I'll tell you what type of rules, how the rules are, how they look like, and they are usually represented in some topos. The topos is like a home for those things. Those who are Greek over here, you might know that the word topos actually means place, and in a way, the topos is like the place for doing mathematics. It's a natural home for where mathematical constructions can live, so to say, and formal languages can be expressed within these higher categories, within these categories, toposes, etc. So so what are types? Now, a type is meant to be thought of here as an analog of a set. You can think of a type as a data type. In a set, you might have undifferentiated objects, elements. So you take a set, you can put any element in it. But in a type, there cannot be any element in a type. A type is like a data type. The elements of the type have to have a particular property. That's why it's called the data type. That's what type means. So an element of a type is part of its nature. So for example, just as an example, if your type is a type of integers, then you cannot put a real number. It cannot be an element of that type. Only an integer can be an element of that type. Whereas if you have a set, you could put an integer, you could put a real number, you could put anything. So a type is kind of constraining what collection of objects you can form by certain properties of that type itself. It encodes that property, and in type theory, you have to first we work with various types, and we work with inference rules that can combine and do operations with types. Just as in set theory, you can do operations with sets. Here, you can do operations with types, and then these operations with types and inference rules will help us to build programs. So, in a way, these formal languages will be useful for literally formally building what I call computer programs or computational routines. Now, how do some of these things get expressed? So there are certain so in a way, think of type theory as a base construction, and you can you have some kind of routine. You have routine objects, and there's not one type theory, so to say. Type theory is a framework for building all sorts of formal languages, and you build the formal languages according to the properties you need. Like you might need certain languages that express logic, or you might need some languages that express natural numbers, or something that does something else. You literally have to build up all the operations from scratch. You have to build up what it means to be a product, what it means to be a sum, what it means to be a number type. Everything has to be built up from scratch, as if the whole of mathematics has to be built up, because if you were to express this thing as a computer program, you literally have to specify every single operation. So that is what type theory is about. So in a way, when you're setting up a formal language in type theory, there are 4 rules. The formation rule to form a new type, the introduction rule to introduce new terms in a type. Those are declaration kind of rules, where you declare a type, you declare a term in a type, and elimination rules of how to use these terms, what kind of operations you can do, and computational rules that tell you what kind of relations might exist between terms of a type. So this is just some notation over here. Gamma stands for a context. That's not the relevant thing. The stuff that comes on the right side of the Turnstile is is the routine statement, is what you feed to a computer or a program, where in the first case is just an example of a type theoretic statement that says that you're declaring a type A. The second thing declares that there's a term A, the small a, in type A, and the next one is saying that given a term A in type A, you declare a type B which depends on the terms of type A. So this will kind of give, with this and a few more rules, you could set up what it means to be a function. you don't just assume a function from our standard definition of a function, but you literally have to say what is the domain, what is the codomain, what are the elements, what maps to what substitutes to what. So it's literally that you have to syntactically build the whole object. And so this is what I meant by a function type. So in this way, what mathematicians do is all objects in mathematics, functions, products, sums, etc., can be built up here. So in this case, think of this, in this example, I'll just walk you through it. If you're trying to tell a computer what a function means, then you first declare that, well, there is a type A and a type B. The computer doesn't know what it is. Everything is to be thought of syntactically. There's no meaning over here. So you have to make everything in a as meaningless way as possible, as syntactic as possible. So you first declare the two types, one that you know, one is going to be a domain, one is going to be a codomain. Then you declare that there is a new type, a function type, which is a different type from type A and type B, and this function type is a map from type A to type B. Then you have to declare that the function type, that within the function type, there's a variable for the type A, there's a variable for the type B. The function with the variable A has to then be a term in the type B, and this term has to then be such that for any term in type B, the variable has to be such that it only happens by substituting A which comes from the domain A, from the domain capital A to as a map through the function to the other side. So you're literally kind of almost in a silly but syntactic way composing every step that the computer will know what it means to be a function, and in the end you declare the computational rule that this particular, so lambda over here stands for a free variable x. This free variable x substituted in this f of a defined above is then the value of the function. So you literally have to specify everything in a kind of very automated sort of way. This is what automated kind of theorem proving works like. These kind of syntactic things have to be specified in such a framework, and this is what type theory is all about. And these are the kind of examples of formal languages that we'll be alluding to. These are slightly more expressive and elaborate languages than purely propositional languages. In a propositional language, for example, you would not have variables and things like that. You might have variables within the proposition, but the basic objects of a propositional calculus are just propositions, and you can have some logical operations between those propositions. Here you might be able to express a few more interesting things and construct mathematical objects. As I mentioned, that these are just some examples, but let's not talk about this now. Now, what is it that I sort of alluded to this notion that these mathematical objects and these so what type theory in a way is doing is trying to do theorem proving, but I've interchangeably been using this notion of theorem proving with programs. So what is this connection between programs and proofs? In fact, this is a well-known correspondence called the Curry-Howard correspondence. Here I'm just giving an extension of it as the Curry-Howard-Lambek correspondence. What the Curry-Howard correspondence was, it's a sort of theorem that comes from computer science, where they are trying to equate proofs and programs. Proofs on the left-hand side and programs on the right-hand side, or computation and logic. And what they try to say is that logical propositions can be associated to types, and when you do theorem proving when you do theorem proving in intuitionistic logic in the setup of constructive mathematics, that is equivalent to a computational process, an abstract computational process, and that's an abstract computational routine. So in that sense, formal computation is just the same thing as formal proof theory in the setup of constructive mathematics, where as you know, in computer programs, there is no real notion of reals. There is what we call real numbers in a computer is just a floating point approximation. Fundamentally, everything is discrete, and that same mapping to proof theory and type theory within intuitionistic logic is what this correspondence is about. And then later people, category theorists like Joachim Lambeck, came up and said that, look, I mean, all these things, we can describe logic and computation, but these things can be nicely expressed within the foundations of category theory, which by that time was already known to be useful for mathematicians. So there are all sorts of categories, like, for example, if you want to express the lambda calculus, there are Cartesian categories that you can express lambda calculus. Quantum calculus corresponding to categorical quantum mechanics, and quantum circuits, ZX calculus corresponds to quantum circuits within the framework of categorical quantum mechanics. There they use these monoidal categories which use tensor products, where the tensor operator, as opposed to the Cartesian product usually refers to the Cartesian product, and the monoidal categories to the tensor product. And these tensor products are objects that are useful in quantum mechanics because fundamentally they are what give you the non-separability of objects in quantum mechanics. I'm not saying that categorical quantum mechanics is all of quantum mechanics, but the part of that subject which is used for quantum computation and circuit simplification is deeply rooted in these monoidal categories, and particularly the tensor product, which gives you this notion of non-separability and so on. So what this correspondence is saying is that on one side you have computation, on the other side you have proof theory and mathematics, and on the third side you have categories and toposes. So it's as if that there are various types of categories that can express various types of computational models and various kinds of logic, and if indeed some notion of toposes or generalization of toposes might capture more general type theories, we might be able to build a deeper connection between these things and express more of these models. Obviously, the missing question is, so where does physics come in over here? This is just speaking about things in terms of this. So one place where people, before I actually tell you where physics comes in, one thing that people realize around more recently is that those who are working on the foundations of mathematics, they said that, look, I mean, when you work with type theory, there is some interesting connections of type theory to homotopy theory. Homotopy theory is a branch of algebraic topology in which you're talking about homotopies between objects. So what is a homotopy? You take a map or a function. Let's call it a map to be more general, and you can ask for things like what is the map between a map. So if you have 2 points, probably I have a slide somewhere like that. Let me just see. It was. Okay, so this slide might be for something else, but what I'm saying still applies. If you look at these diagrams, then in the second instance you have a map between 2 objects. In the third instance, you can ask this question: what is the map between those maps? And that's a homotopy, and it's a continuous deformation of one map to another. And then but this doesn't stop there. A homotopy can go to any order up and up, and this is what type theorists at that time realized, that there is some deep connection between types and homotopy spaces, because in type theory you have a type and you have some terms. If you have 2 terms and you want to know whether they are equal or not, you would have a proof between those terms. But you can have more than one proof. So they quickly realized this connection to homotopy theory, where a proof between 2 terms, so think of a type as a space. You have a term in this space, you have another term in this space. If you want to prove that they are equal, you'll construct a program. That program takes you from year to year. So it's a path. The program, the proof is a path between those 2 terms. If you think of this analogy of topology to types. And now, what if you have another proof, which means you have another path? Then you have to ask the question, are these 2 paths equivalent? They needn't be, according to homotopy theory. Then you need a proof to show that one path is equivalent to another thing. And if there are more proofs of that, you can have all kind of hierarchies of homotopies and so to say proofs of proofs of proofs. And mathematicians quickly realize that type theory, along with its proofs and hierarchy of proofs, has this very close intuition to homotopy theory and topology. And they made these analogies, the one that I alluded to over here, that if this is a type and there are 2 terms that you're trying to prove whether they are equal or not, you have proof P, you might have proof Q, and you might have a homotopy between those things, which is telling you how equal is the proof P to the proof Q, up to what, and are there more ways to do that? So similar to that, they realize that all kinds of things in type theory have some analogy to to some spaces and homotopes. Even things like products of types have some kind of intuition of a product space, and you have other types that relate to sections and fibrations. So a lot of these intuitions from topology seem to apply to type theory, even though type theory is just an abstract symbolic system. It's just a formal system. So what is happening over here is that instead of thinking about topology, so how do mathematicians usually think of topology? They think of a space, and on that space they do all kinds of constructions to probe that space. You might construct paths between that space, you might construct paths between that space, paths between paths, etc. And then according to those properties of those things, you say, okay, this space behaves like this. What is happening here is that whole logic is being reversed. Instead of trying to talk about spaces and then talk about what things happen on that space, they are thinking of paths and homotopes as the fundamental thing, rather than the space as the fundamental thing, and saying that according to the properties of what homotopes can do, spaces should be defined from that. So it's like a reversal of logic. Instead of talking about spaces and then talking of maps and homotopes, you think of those homotopes and maps as fundamental. And in type theory, because there's a very natural notion of how homotopes can be expressed, there's a kind of very a deep way, kind of interesting way in which you can now speak about types, propositions, programs, and try to associate notions of topology and spaces to it. So how does that go? So let me tell you two things. Let me tell you how physics might come in, and how mathematicians might actually use that intuition that I just expressed in type theory to come up with more serious ways to actually construct spaces from types. How am I doing on time?
Okay, let me check. So 11:30 will 11:35 would be where to end. So 5 minutes, 5 to 10 minutes.
Oh,
So you
okay.
started at 10:50.
Okay.
So 10 minutes.
Okay. So all right. So far I've spoken about programs and proofs. So I'll give you a kind of intuition of where the physics part will come in. What will happen is that in the earlier work with where there was some physics, there was only kinematics, there was no dynamics. So the place where dynamics will come in is that proof systems in a formal language will be the things that will realize the dynamics for us. This was what was missing in Ishem's work. They were not working with proof systems. They were only making kinematic assertions. So in those kind of formal languages, if you now admit proof systems or proof calculi, that makes the language richer for purposes of mathematics. Those will also give you some interesting physics, in the sense that what will happen is that laws of evolution of dynamics or of a physical system will correspond analogously to computational rules or rules of inference, and dynamics itself will correspond to theorem proving. So or the execution of computation. So in a sense, the execution of formal computation is physics in play. Physics is like nature with its building blocks, with its pre-geometric fundamental building blocks, doing steps on its own, and that's what will be a realization of dynamics. Now, obviously, I'm not trying to tell you that all of physics, you write down Newton's laws or Schrödinger's equation, you just get it like this. That's not the statement I'm trying to make. I'll have to give you a kind of clarification of how far you can get by using proof calculi to build models of physics, and when you want to do more interesting things like quantum field theories, what additional mathematics might be necessary. And fortunately for us, a lot of such ideas have been developed in various mathematical physics circles. So I'll allude to what work is going on to not just speak about the main question of this talk, which is where do spaces come from, but how you can do interesting quantum field theories and other things on those spaces. So okay, so this slide summarizes what I just mentioned. The primitives of kinematics and dynamics will be propositions within the formal language and some proof calculus that you have to admit upon this language to give you the primitives. But what can you, let me give you a few examples of what these proof calculi are. I've just mentioned about them, but I've not given specific examples. So I'll just throw a couple of examples. This one is not one that I'm using particularly for what's following, but it's worth mentioning. In categorical quantum mechanics, there's the whole ZX calculus, which is a diagrammatic proof calculi for constructing quantum circuits. Essentially, these green and red blobs are known as red spiders and green spiders. They correspond to block spheres of the poly Z and the poly X operators, and these are just diagrammatic rules for now with these think of this as a tensor network, and these as rules for the basic blocks. And every quantum circuit can be expressed in this way using this calculi, and then you can ask whether two quantum circuits are similar or not by doing some rule simplification. So this is one diagrammatic calculus that people use in quantum circuit computation. This is the work of Bob Cocker and several others in the group in Oxford. And another, this is the same thing. Another example of a proof calculi is rewriting systems. Rewriting systems are well known to computer scientists. There are all sorts of rewriting systems. The simplest are what I call term rewriting systems, where you have a set of rules which means that whenever you have something on the left-hand side, if it matches any of the rules that are given, then you substitute it with the right-hand side. And here is an example of how you can build a program for adding two numbers by using these simple rules. So as you know, to add two numbers, you use these successor functions. They correspond to some numbers, and just by using these rules of piano arithmetic for addition, if you have 2 plus 2, when you have two s's, the number of successor functions is the value of that integer. 2 plus 2, if you just substitute all these rules and you go through, you get 4. Nothing has been put in over here by meaning. You're just using mechanical rules to do addition, multiplication, and so on. So this is a simple example of a term rewriting system. The more interesting rewriting systems that we'll allude to, this is coming from the work of Stephen Wolfram and the Wolfram physics project. These are graph rewriting systems, where you can have some initial graph and you have some rules. So now the rules are not terms, but they are subsets of graphs. Wherever you see this subset, you just substitute it with that subset. So given any initial graph, you can substitute these rules and you can start building up what the rewriting sequence is. This is another example of a proof calculi. In this case, you might want to know whether an initial graph is isomorphic to some other graph. So in order to do that, you mechanically have to do these substitutions and ask if one object is equivalent to another. So this is what is used in automated theorem proving as well. Those kind of methods. This is an example of hypergraph rewriting systems. The same thing can be done with hypergraphs, and essentially these. So how far can we go with these primitives of kinematics and dynamics? Because these are very simple, basic things that I mentioned. They are not kind of having enough structure to maybe write down quantum field theory. So the idea is that all the examples I've shown you are the kind of things that you would use for combinatorial or pregeometric models, very simple models that are based on primitive building blocks without assuming continuity or so on. And then there you could use a formal language, you could use some symbolic construction, and you could use some proof systems to build up. The reason I mentioned those is because some of those rewriting systems will be directly useful to relate to current day theories of quantum gravity. But just to give you a kind of word of warning, if you want to do more interesting things, like you want to express quantum field theories on generalized spaces, so on, one also has to do a little more work to show that this framework of formal languages has enough potential to express more complicated structures, like mathematical structures, where you might come up with general notions of cohomology, Lie algebras, and so on to express quantum field theories. Luckily for us, some recent work of Urs Schreiber, Mike Schulman, and others in the context of homotopy type theory in what they call cohesive toposes allows for these generalized spaces. If we have time, I might mention that. Otherwise, those are things we can discuss later. But this is just to give you a kind of heads up that there is some more recent mathematics in what are called higher categories, and not just categories, but higher category theory, in which you don't have just maps, but you might have maps between maps. So essentially, when you take this idea of homotopy seriously, you can not only kind of enrich type theory to homotopy type theory, but you can also enrich categories, not enrich is the wrong word, but you can also equip categories with maps, between maps and so on, to get higher categories. And in that context, people have realized that that gives you the right kind of mathematics for seriously talking about the kind of extended objects and spaces that you might see in string theory, M theory, and other things, where you might be able to describe quantum field theories in general spaces. So those kind of things now exist. Of course, what I'm still going to focus over here, not on the infinity toposes as they are called, but on the kind of things that are relevant for pregeometric models. So in a way, this is the kind of idea I alluded to. You're asking, where does physics take place? It takes place in some suitable topos within which you can express a formal language. There's a kinematics part to it and a dynamics part. The kinematics has to do a lot with the locality properties, which means locality properties involve how you can glue local parts of that category of that topos together. And the kinematics consists with what type of paths you can connect. And paths are the proofs that we mentioned, because if you have the relevant proof calculus, a path is a proof or a program. So these are the kind of abstractions of what kinematics and dynamics would be on these constructs. Now, just to give you an idea of how this will be relevant for quantum gravity. Quantum gravity has a huge landscape. I'm just taking a few examples that might be relevant to the audience here. I'm not trying to cover all quantum gravity theories, but if we take a few interesting examples of some prominent theories, causal set theories, causal dynamical triangulation, spin networks, matrix models. And obviously, you see all of these are based on pregeometric kind of ideas. They are all using some combinatorial models, operator algebras, etc. So the question you can ask is that if indeed there is this framework, this structural framework to express various theories of physics via these formal languages, can we express some of these existing models within these kind of formal languages? What type of formal languages, or what type of proof calculi would you be able to use to say set up a causal set, or to set up these set up some kind of Lorentzian triangulations or spin networks or matrix models? So that, I mean, it's not like there's one universal answer for all of these. One might have to take these things step by step. So for instance, what you might do is, I showed you an example of graph rewriting. In graph rewriting, indeed, you might be able to build causal sets from graph rewriting by keeping track not just of the graphs that evolve, but also the information of causality. So causal sets can in fact be constructed from a graph rewriting procedure. I also showed you some procedure for hypergraph rewriting. Those hypergraph rewritings with additional constraints might be able to give you at least some diagrams that you see in CDT, where you have Lorentzian triangulation. So instead of trying to, here the idea then would be not to take a space and triangulate it, to take triangles of tetrahedrons, or depending on the dimension you're working with, and build rules to glue them together to build this discretization. Of course, this doesn't mean anyone is replicating CDT or causal sets, but it's just to say that within those models, there is a way to see them as something that could be formalized in a formal language. And similarly, for spin networks or matrix models, you could think of the correlation functions of matrix models, which are the ribbon diagrams, through some kind of diagrammatic rewriting. And for spin networks, you might think of them as tensor networks in some group-valued operator algebra. So there are some simple ways in which you might be able to think of these many of these models in a formal language framework. You might also ask, what's the use of doing that? Why would you do that? So I'll give you two kind of answers in that. One is that if you express some of these models in a form in the framework of some formal language, it might make it more illustrative to actually start comparing properties between these various quantum gravity models. And the second thing is, by expressing it in this formalism of formal languages, and using these connections to homotopy and topology, one might be able to actually answer this question, where spatiality comes from. In many existing models of quantum gravity, the usual practice, of course, I'm not saying it's incorrect, but that's the way a physicist would do this. You would try to take some appropriate continuum limit and get some notion of spatiality. But if you ask a little bit deeper, why does space just come out of it? What is there to, so what if you take the continuum limit? what is it that fundamentally leads that spatiality in it? So there you could start asking the question that if you express this thing in some type theory, in some formal language, and you use the properties that they are these homotopies, this tower of homotopies is then associating to some topology, and that is why space even comes out of it. And in a way, this reasoning is also the thing that mathematicians more recently have been using to kind of say why the notion of space even comes in mathematical objects. So that same idea could be used for even physics. Now I'll just give one example in which I don't know how much.
You're kind of over. You're eating into question time.
Okay.
So 5 minutes of questions after this.
5 minutes of questions left.
And 2 minutes. 2 minutes plus 5 minutes for questions.
Okay, then let me just take 2 more minutes. Let me skip this part. Okay, fine. I know what to skip. So let me put it this way. So here is. I'll just give you one quick result that is there. The details we can always discuss later. We are here for the next few days. One of the things, as I mentioned, is that by expressing these quantum gravity models within these formal languages, you might be able to say why space comes from. So let's take a concrete example to see how mathematicians describe these notions of spaces. So here is an example of a rewriting system where which is a kind of non-deterministic rewriting system, but in addition to the rewriting terms, you're also keeping track of the arrows, which are the causal edges. This is called a multi-way system in the context of what is the Wolfram model. Think of this as a graph rewriting system. Now in this graph rewriting system, you can continue doing this rewriting ad infinitum depending on what this system is. You might now start asking the question, so if I take this if I want to express this as a formal language and ask about how properties of space might come when I take some continuum limit, how would that work? So the first thing would be to express that whole system in terms of types. Now let's not go through details of the types. I mentioned to you that there are several things, graphs and several objects that you can express in type theory. These would be the rules for that. I'll skip that part. But once you express all that as types, what can you do? Now, what mathematicians have been doing is, as I said, once they realized this deep connection between homotopy and types, they started thinking about it this way: that when you have a type theory, rather that corresponds to some mathematical object, rather than talking about it purely in terms of set, in terms of set theory, you might discuss it in terms of what are called homotopy spaces in mathematics. And there is a deep connection between that, and through that, mathematicians have come up with the notion of why a Lie group might even get its spatial properties. So that same idea is closely related to what is called the Grothendieck hypothesis, where the notion of homotopies is closely related to topology. And let me also skip this slide. In the example, in the rewriting system I showed you, if you continue this process, you start building homotopy cells. You can not just build paths, but you can start doing rewriting with higher order rules and start constructing paths between paths. So what I'm trying to do here is I'm trying to give you a computational example of that realization of what mathematicians are talking about, the connection between types and spaces and homotopy spaces. In homotopy spaces, you have homotopy cells, and here by computationally rewriting these types, you can start building these two-dimensional faces, three-dimensional faces, and so on. Essentially, those faces are higher order morphisms in some appropriate category. And when you take the infinite limit of that, that maps to what is called these infinity groupoids. So this kind of homotopy theorem, where the infinity limit of those higher order maps to some topological space, one can also see a computational realization of this. So in a sense, in quantum gravity models, when you express it in this framework, this is the reason why these higher homotopies are the reason where the notion of where spatiality even comes from it. And what that means is, this is the last slide, the summary of this is that compared to, so here, when I showed you the Curry-Howard-Lambeck correspondence, I said, where does the physics come from? In fact, so in a sense, you can take this picture as a summary to answer that question, where on top you have this correspondence, in the computer science correspondence between proofs and programs. Over there you have this mathematics, foundational mathematics correspondence between proofs and homotopy spaces. And more recent work people like Schreiber and others, connecting homotopy spaces to higher differential cohomology and higher categories to physics. So in a sense, constructive physics is just this whole tour from type theory to homotopy spaces to physics. So the deep connection between physics and computation comes by understanding all this chain of correspondences in physics, mathematics, and computer science. And within that, you can this way of thinking gives you a sense of how to think of spaces in physics, and also when you have various models of quantum gravity and you want to ask what type of field theories or what kind of symmetries you might have on these generalized spaces, then this might be the kind of way to constructively discuss them and to also build the right kind of mathematical tools to analyze them, in the sense that if you're looking for what type of extended objects might sit in a space, you want to compute some cohomology classes of those. So those, now you would have to talk about not just cohomology classes on a manifold, but cohomology classes on a homotopy space. So that would be a little more general theory, and some of those things are now only in the past few years people have been developing it. So this would be the way these things would link up, and that I should just stop.
Okay, I suggest one question and then further questions over coffees, because we're sort of running quite a bit over. Who was first?
I think it was, yeah.
Oh, hard task. I'm not pretty, convinced by your reasoning on the relation between the formal language and physics, because from the physicist viewpoint, these are like we say different layers. Okay, you have a certain physical degrees of freedom, and then you have a certain dynamics, and this dynamics can be formulated as a certain proof-making language, starting from a certain set of axioms, proving eventually a certain theorem. Okay, and from your perspective, you somehow treat the language as something fundamental, something what you.
I'm not making any ontological statement. I'm not trying to link it to the ontology.
Mm-hmm.
I'm just saying that formal languages give you a framework for describing theories of physics where you can have generalized spaces, where theory of physics discuss in generalized spaces. So this is literally a structural framework for building theories. It is not meant to be. It would be an interesting philosophical question, but I don't think we have enough tools to answer this at the level of ontology. For example, as you see, in many theories of physics, people start with an ontological statement. They say there's strings, or there's loops, or there's this. These are physical objects, and then we give them properties, and then we do things. Here, we are not trying to say anything at that level. We are saying that if I want a theory of quantum gravity of one sort or the other, what are the basic symbolic sets, the symbolic objects, the basic words, formula, etc. I can build that. So we are not trying to say what of this language may or may not be ontological. I'm not worrying about that point. In fact, when Wheeler had this idea in mind, he was saying that we should not start with any physical ontology. We should just take language as something abstract. So Wheeler did have in mind that this abstract language might have some ontology. But over here, I'm not sticking to that, because I don't think we have. One can debate, and it's an interesting philosophical question, how far it might be that that physics, the physical universe, comes out of this ontology. Is the same thing like saying these are the equations, but what gives it life, or what breathes fire into it? We are not talking about that part. We're just talking about how theories are structurally formalized and how you might find some common framework.
From this perspective, this is fine, and I would like to understand also the utility of this framework, and I would like to ask you to comment whether within this framework of the formal languages, you can in particular prove Turing completeness of certain types of the dynamics, which might be present in case of quantum gravity models.
So
you talk about that, because usually, if you have a formal language of a certain type, you can try to associate the completeness of that language and that would be, specifically interesting in the context of gravity. Okay, whether a given dynamics correspond to something that can be computable. Okay?
Exactly. I mean, that question, of course, is interesting, and as such, formal languages should allow you to at least ask and address those questions. There are a couple of interesting issues there. One is that just as formal languages or programs, you have certain quantities that are computable and certain quantities that are not computable. The same things you might ask in physics: what does it mean for something to be computable and something to be not computable? In many ways, what is behind this notion of computability and other things in formal languages is the notion of the observer. There'll be more talks on that later. In a way, this framework is also kind of inherently requiring, this framework of formal languages and constructive mathematics is requiring that there is some notion of observability. You cannot just say anything. And in many ways, physical, I would say, to answer this question in a kind of short way, physical observables are those that require, that are observable because there is some observer, and they are computable in the same sense. They are computable because there is an observer. And things like whether some dynamics is Turing complete or not will then require taking into account what is the system, what is the observer, what is computable, what is not computable, and then making those statements.
Maybe just last comment, concerning the terminology that you refer to, namely that pregeometric concept is used in at least two different meanings, and in quantum gravity, this is the one that you are referring to. However, in quantum gravity research, if you have a certain different configurations of the gravitational field, okay, they might be also considered pregeometric in the sense that they do not reflect typical geometric properties, like I don't know, for instance, ultra local phase or other phases of gravity. And then you have a geometric phase with regular geometric properties. So this is just a comment that this term has at least double meaning.
Right,
okay?
right.
Just to be careful. Okay?
Right. Though here, when I'm saying pre-geometric, I'm literally meaning no geometric information. A lot of theories that of quantum gravity might still assume some geometric information. Here, in this formal framework, there is no geometric information, and the key point is to note that there is a way to show how geometry might be realized or might emerge from this abstract construction. And that's why it is pre-geometric, and these building blocks, the types are the building blocks from which you can build spaces and give a notion of where spatiality comes from. But indeed, there are other ways to describe that term.
Very quick.
Can I just make a quick, just because my question was related to this discussion about decidability and the relationship between theorems and the relationship between theorems and states. So that reminded me of a paper from Chancellor Brook, and there's a couple of papers from about 10 years ago, where they make a relation between theorems and not states, but observations, there is outcomes of measurements. And so then if you think of it that way, then you can make an analog of Chaitin's incompleteness version of Wilson. Right. And then they can make sort of an analog of undecidability, right? Where quantum randomness arises out of undecidability, which you can think of as due to the fact that the information content in the axioms is smaller than in the total information content of the possible sets of propositions that can formulate, you can ask.
Right.
But then there will be a sort of different connection instead of relating theorems to final states, you're relating theorems to final observation outcomes.
Yeah, that's fair enough. There are ways to still think about that within the framework of a language in a way.
Yeah.
Okay, thank you. All right, I think we're going to have to do a global time shift of like 10 minutes and start 15 minutes. We've got a buffer at the end of the day. Eric, did you want to try out your laptop given the shenanigans we've just had?
I came across you. You've been organized in the complex systems conference.
Yeah.
Right.
The question is a little bit related to this undecidability and what it means in this framework. We published on this topic as well. I'll send you the paper later on in Physics of Life reviews a few years ago on the line paradox and stuff. So I just want to clarify a few things. So say that the Russell set paradox, right? We consider the set of all sets which are not members of themselves, right? So that was obviously paradox in the naive set theory, and Zermelo and Frenkel resolved it by not requiring the comprehension assumption, pretty much by saying that, well, you know, the Zermelo approach and all axiom choice. But I understand that the type theory is also a resolution for the paradox, because in type theory an element could be a member of only one type. That's why you cannot construct this type of paradox, because there you say this set is a member of that and this set is a member of that. Right? So in type theory, you can construct something which is a set of a type of all such types. Yeah, but it cannot be included in paradoxical. So if that is the type theory, that's what you use. And it will have some notation.
Are you Unity tomorrow?
Sorry?
Are you Unity?
Oh yeah, I'll be here. Yeah, I want to come and hear you talk, and I want to hear some other stuff.
Jules, we're going to grab coffee if you want to join.
Yeah.
1 second, sorry.
Coffee cup.
Do you understand when are we coming back? When are we starting?
15 minutes.
All right.
Yeah, it
Any
looks like
luck?
it's fine.
No, same problem, is it? Is it the same problem?
Oh,
That was the
you
problem.
said what's that from?
That was the problem.
So you are, for some reason, a different one of these.
I have one
So
of
it might
those.
actually be
That
this.
might-
That's the, oh, hey, this is.
Is it just
it's
back
faulty.
connection?
It's faulty, yeah.
I have another one.
No, it's fine, as long as you're not kind of shifting anything around. Wait,
Let's try that. Might be a bit more.
that's good to know that. Everything will be fine for them. They always go very quickly, these a few of those guys. So remind me on your the logistics of what you're going to talk tonight or tomorrow?
Tomorrow. Yeah, it turns out it's going to be too late. It's going to be this on Saturday night. Actually, I want to ask you because when you try to do online, I was going to ask if, because I tried to test it from the hotel, but the Wi-Fi is horrible. I don't think I can give a talk there. Do you know if there's any
Is there a possibility of what time is it?
between 7 and 8 p.m.
You're welcome to use my office. I'll use it with key card. If you're going to my office at 6:30 or something, I'm going to just lock the door and leave it. Oh, there we go.
There's no other cable, there's no VGA?
From my version of this thing. How can we not be over this one? We've got near sentient AI. There we go, okay.
You don't have like a slide shifter that like when you touch the laptop, do you?
You've got Wi-Fi. Use Keynote, it's just a connected software, just in the next file. So you install Keynote on this thing.
Then we have to also use Keynote.
Oh shit, I didn't stop the